Good afternoon, and welcome to the launch of the second report in the Emerging Technologies Institute's flagship study, Directed Energy Supply Chains, Securing the Path to the Future. I'm Dr. Arun Serafin, Executive Director of National Defense Industrial Association's Emerging Technologies Institute. We're joined by an extremely distinguished audience, both in person and virtual, and I'd like to thank you all for coming. ETI was established in 2021 to bring NDIA's unique perspective into the conversation of how emerging technologies are creating the future of national defense. Our activities span the range of all emerging technologies areas, but also include the policy environment that shapes how industry and government can develop and deploy the systems of the future, including acquisition policy, workforce issues, and budget. Today's event and report are just one example of the type of activities that we are conducting here at ETI. Our team also has a drumbeat of other activities ranging from reports on modernizing defense microelectronics, enabling the joint warfight, the state of the space industrial base, and many others. Also webinars and podcasts on topics ranging from DoD's S&T budget priorities, 5G and Future D, quantum computing, to the Defense Civilian Training Corps and everything in between, as well as our major Emerging Technologies Conference that we are again holding this year, August 7th through 9th at the Washington, D.C. Convention Center after an extremely successful debut event last summer. As part of this directed energy effort, we're also creating a directed energy source book designed to provide a publicly available index of companies related to directed energy working in that space. If you're interested in having your company included in the source book, please reach out to us via the website or speak with one of our staff members who are all here today. I encourage you all to look at our website and our YouTube channel to see all the things we're up to and subscribe to our mailing list to learn more and keep up to date constantly. For today's event, when ETI was created, we set out to assess the state of defense emerging technology supply chains, while also educating the system on ideas for their development, health, and resilience. Our first report focused on hypersonic supply chains, and we launched that last May. We've seen that report generate discussion throughout government, industry, and expect today's report, Rebecca, to do even better, talking about directed energy. And we believe the key findings and recommendations found in these reports can substantially enhance the security and reliability of our critical technology supply chains. Those are technologies that are mature enough, but we have to be sure that we can actually produce them at scale and at the speed that we need. And we look forward to sharing our findings with you all today. Some administrative remarks before we begin. First, you can access the report at emergingtechnologiesinstitute.org/directed energy, and in a link that should be on your screens now. For your awareness, the event is being recorded. You're welcome to record it for your reporting. We encourage our online participants to please submit questions via the Q&A box for both our keynote speakers and our panelists. For those in person, we'll have mics available. Please wait for the mic to ask your question for the benefit of the online audience. For media members, please include your name and publication prior to asking your question. Finally, most importantly for everyone, for those who are in person, please see Daniel Park from the ETI team in case you need a parking pass to exit the parking garage. That's definitely the most important thing. Now, we'd like to hear from my boss, NDIA's President and CEO, the Honorable David Norquist.
Well, thank you, Arun. Good afternoon. Thank you all for being here. We're very excited to launch the second report in ETI's Emerging Technology Supply Chain Study. ETI's activities fit well within the range of NDI's robust set of programs, publications, and conferences, where we try to focus and elevate the government-industry dialogue on how together we can support our warfighters today and win the technology race for the future. The development of the current generation of advanced directed energy weapons comes at a critical time of great power competition and increased geopolitical tensions. Recent global conflicts have repeatedly demonstrated the necessity of having weapon systems capable of countering the most pressing emerging threats at low costs with high success rates. The technology advantages granted by directed energy weapons and other emerging technologies are absolutely imperative to deter and decisively win conflicts. And ETI is playing a fundamental role in taking advantage of and promoting these advantages. However, in order to succeed, directed energy weapons must be supported by a secure and resilient supply chain. As many of you likely seen, the importance of supply chain resilience was made abundantly clear in the recently released DoD report, the National Defense Industrial Strategy. From mining and processing critical raw materials to testing infrastructure, workforce, and the manufacturing of key components, each tier of the directed energy supply chain is critical to maintaining our competitive advantage. If we approach this challenge with the proper dedication, we will provide the next generation with the tools to triumph in a future crisis. Now, NDIA has been around for 100 years, and we are planning on supporting through the next 100 years of America's national security. I'm honored to welcome our panel, our distinguished guests, and to have everyone here and online join in the discussion. So welcome, for those of you online, welcome to NDIA. I'm now honored to introduce our keynote speaker, Dr. Frank Peterkin. Dr. Peterkin is the Principal Director for Directed Energy at the Office of the Undersecretary of Defense for Research and Engineering, and he will be discussing the future of directed energy weapons for the Department of Defense. Ladies and gentlemen, please help me welcome Dr. Peterkin.
All right. So thank you to NDIA, all the staff members, Honorable Norquist, Dr. Serafin, for giving me the opportunity to kick off this conversation. I really appreciate the effort that NDIA has putting into looking at my space, at the direct energy community, at the challenges we face. I've had a chance to look at the report in advance, and for those who are going to start to get to see it, it's a lot of work that you put into this. A tremendous number of communities that you've managed to talk to through industry, academia, and government. Well thought through conclusions. I assume you're going to be going through them here shortly. And they're going to generate, I think, a lot of interest and engagement in the future. But for now, what I've been asked to do is give kind of a run through of where we're going with directed energy, what is directed energy, where are our priorities, where do we see the prospects for capability for the U.S. warfighter in the near term. So again, I'm Frank Peterkin. I'm the Principal Director. I'm one of 14 Principal Directors for the critical technology areas that the DoD has identified. I support Honorable Heidi Shue, the Undersecretary of Defense for Research and Engineering, and also Mr. Maynard Holliday, who's the Assistant Secretary of Defense for Critical Technologies in OSD-RNE. Go ahead to the next slide. I thought I'd give just a quick intro for those who aren't living the day-to-day dream of directed energy. Usually we talk about primarily high-energy lasers or high-power microwaves being the technologies that provide the weapon capabilities for directed energy. Why do we care? Lots of shifts in the threat environment over the last 10, 20 years. Not that threats are new to us, but the proliferation of lower cost or more stressing threats has really become a significant factor in thinking about how we protect our forces. Swarming capabilities, I think we've all seen evidence of that. You can just look at the holiday celebrations of UAVs dancing in the sky and imagine that those are not so benign in other circumstances. We've faced threats in all domains. The ability of adversaries to know what we're doing, where we're doing it, has been growing. Technology, the pace of growth and adaptation of technology and its affordability is much different than it was previously. And the threats that are becoming so stressing, both in their sheer number, the intensity or the rate at which they can come at us, and in their maneuverability. It becomes a challenge for our more conventional or traditional kinetic systems to maintain an overmatch on an adversary that is pacing or maybe in some cases exceeding our capability. And so how does direct energy help? Well, first of all, the missions that make sense for us now and in the future, some version of integrated air and missile defense. That could be counter UAV, that could be counter missile in a variety of profiles and domains. It could be for countering UAVs or other asymmetric threats, where again there's a cost advantage or a maneuverability advantage. And then there's some capability that we bring for countering sensors that is sort of unique opportunity that direct energy brings to the fight. And why do we have advantages? Well, we all tend to tout the fact that direct energy is basically electromagnetic radiation, whether it's light or RF energy, and therefore it travels at the speed of light. For those of you who haven't looked up your physics books recently, for comparison, we talk about hypersonic threats being really, really fast. That's somewhere in the 5 to 15 Mach range. The speed of light is about 100,000 times faster than anything we or anybody else is fielding with hypersonic systems. It's really fast. And that means it can touch a threat or a target nearly instantaneously. That doesn't necessarily mean we affect it instantaneously. There's oftentimes a dwell time required. So you can imagine direct energy being essentially the symmetry or the compatibility with conventional kinetic systems where we have finite fly-out times to the targets and then fairly quick interactions. We have very, very fast interactions with the target, and then it takes a while to cause effects. But that speed of light engagement is what particularly allows us to take on maneuverable threats, because we can move electromagnetic beams much faster than we can ever move a defensive missile, for example. So that speed of light is a big factor. Relatively low cost per shot. We're not necessarily low cost per system that we buy. That first shot can be a little pricey, but the second and beyond shots are significantly cheaper, and they offer us significant advantages for the warfighter in terms of the resilient logistics that comes. As long as you have electricity, fuel of some sort, then you have a weapon. And that is not always the case with conventional systems in almost any domain. Deep magazine, because we're based on electricity, the precision tracking, the opportunity to dial a knob up and down and graduate the effects. That's another unique attribute that we don't typically get with conventional weapons. They're almost binary. You shoot a missile, it either defeats a target or it doesn't. There's no knob to turn up and down on a missile. We have that opportunity. And for example, if you have a high power laser weapon on a platform and you know you can defeat a threat at a lower power level, then you can dial the knob down, and therefore you have less impact on your platform operation. And then the last piece that's very unique to laser weapons in particular is a laser basically has a telescope that we use backwards. We call it a beam director, but it's a telescope. And so 99% of the time when we're not using a weapon, we still have an astronomy grade capability to surveil the local environment, augmenting what we typically already have with sensor systems like radars. And that, as we have already found with systems that we've employed in several services, is in fact what happens. It's used constantly for surveillance capabilities. Let's go ahead, next slide. So Dr. Serafin asked me to give a little sense of where we're going, and so everybody's strategic vision is always aspirational and maybe unachievable, but ours is deliver the unique advantages of direct energy technologies to the U.S. warfighter for missions across all domains in which the Joint Force operates. That's a mouthful. That's a lot, but I think there's a significant element of viability to that statement. We won't be able to talk about all of those concepts and activities that we have going on in this kind of forum, but I really do drumbeat that there is an opportunity here for direct energy in all domains of the Joint Force. Next slide. So if I only had one slide, it would be this one. This kind of sums up the where we're going and how we're going to get there in direct energy for the DoD. In what we call the roadmap. All the principal directors for the critical technology areas are required to develop this sort of roadmap to help guide the technology investments as well as the implementation of systems across these areas. And so we all have slightly different ways of articulating it. We call this a stair-step chart. My predecessors in the position developed this, and I've maintained continuity of their approach. I think it's a solid approach. It boils down to crawl, walk, run. the lower left of that stair step in the current time epoch of 2019 to 2024-ish is basically do what we can today with technologies that are mature and available and moderate in cost to develop systems and employ them to learn what it means to fight with these sorts of systems, how they interoperate and integrate with the rest of the force, with the platforms that they're positioned on. And that is happening today. I don't have time in today's remarks to go through the laundry list. Some of them I think are captured in the report that Dr. Serafin will describe. There are a tremendous number of systems. In the last 10 years, we went from one laser that the Navy had employed roughly a decade ago to the many double digits today. So that's a real sea change that's been happening in these last 5 years. Do what we can, countering UAVs, countering surveillance systems, artillery and mortar, and some counter ISR capabilities. In the midterm or near term 2025 to 2030 timeframe, we still need to develop technologies, and we are doing that take on the more stressing mission sets, like countering cruise missiles, whether they're land attack or anti-ship. And both the Army and the Navy, along with OSD, are heavily investing in those technologies to bring that capability to bear, particularly through both system demonstrators and then experimentation to show that we can, in fact, defeat missile technologies or defeat missile threats. And then in the far term, upper right, we hope to get to the point where we have a more strategic impact, where strategic means essentially the even more stressing threats, supersonic, high diver cruise missiles, ballistic missiles, maybe hypersonic missiles, et cetera. But that's going to take some significant maturation of technologies, probably fix some of the, or address some of the concerns and issues raised in the kind of report that NDIA has put together. That's going to be a harder lift. But the first two elements of that stair step we are actively pursuing today and having a great amount of success. Next slide. So what does that all mean? What it means is we're investing in several priority areas for the science and technology aspect of the sources for direct energy. That's high power lasers, that's high power microwave systems, the control mechanisms, the beam control systems, the beam directors for laser weapons, or the antenna systems for the microwave and RF systems. We invest a lot of effort in understanding lethality and vulnerability. These are new weapons being brought to bear on new targets. So there is a lot of effort that we go into to understand, can we cause effects? Can those effects be caused in a manner that is useful to the U.S. military? Can they be caused in a timely manner to achieve a mission? A lot of investment there. We identify power and thermal management, and I think that's also captured in some of the reports you're going to hear about, as a priority area, although the direct energy community itself is not going to carry the load for that. There are too many other capability areas where power and thermal matters, including a lot of commercial, obviously, applications for highly dense battery sources or novel ways of managing thermal energy. So we identify it as a priority area for the roadmap, but we're not going to carry the heavy lifting on all the investments for that. Now that's the S&T piece, which gets a lot of attention because it's the shiny widgets. But realistically, in the Department of Defense, you can build all the shiny widgets you want. You're not going to transition unless you address some other issues, like how would the operator use your system? And we're getting after that today through prototypes and operational experimentation. The services, in particular the Army, the Navy, and the Air Force, have put systems forward, and they're not always perfect, but they are in the hands of warfighters who are figuring out ways to use them in situations and scenarios which maybe we didn't initially envision, or we're discovering that we do have some shortfalls in our systems that need to be addressed through additional development. I'm not going to spell out every word in the .mil-PFP acronym. You can look it up, but there's a lot of things that happen when we field systems, doctrine, organization, training, et cetera, that have to come forward if we're going to field weapons, and that has to go hand in hand with the decisions to buy them and build them for the future. We have to do a lot of mission engineering and operational analysis. If you're not familiar with that term, basically it means play the fight as it would be played in mission scenarios and modeling and simulation, and then understand what that implies for feeding back into the requirements and the specifications of those systems. And that's where we really start understanding the value proposition. play a fight with direct energy, play a fight without direct energy. Hopefully things have changed, and hopefully things have changed enough that the value and the cost of the systems is worthwhile. I think it's going to be near and dear to the NDIA folks that the industrial base and open architectures is on this slide. We didn't game this. This is my roadmap. This is not NDIA's. But industrial base and architectures is extremely, extremely important for our community. And hats off to the companies and the organizations that are hanging in there while we decide at the DoD level, when we're going to actually procure them in numbers. But we need that industrial base to be healthy. We need that supply chain to be healthy, and we need to figure out how to do architectures that foster competition in the vendor base without oversubscribing their ability to innovate, new capabilities to deliver to us. And then a drumbeat that kind of gets lost is because we're a new capability for directed energy systems that's novel and not the way we fought in the past with more conventional kinetic systems in particular. We need to figure out how to do command and control in a different way. There are going to be some uncomfortable choices when we bring these systems forward, where commanders who would normally shoot a missile, say relatively far to take on an incoming threat, but might have to decide, I trust that the direct energy system will in fact engage and defeat that threat, and I can reserve my more costly and more capable missile for defensive applications and other parts of the threat space. So command and control integration, all of these have to get addressed in parallel and as a community for us to proceed to be true capability for the warfighter. I think I only have one more slide, and hopefully I'm roughly on track for time. This is a busy slide, and I don't know how it's playing on the virtual world, but just pay attention to the main titles here. In order for us to transition and to focus on the things that enable that, 5 areas of us for particular interest: how we implement. That's across the kill chain. That's across the .mil PFP that we described earlier. Do we have the workforce and do we have the infrastructure necessary to support that development? New weapons, not necessarily, and I can go through a whole laundry list. Safety communities in the services that don't have familiarity with the particular use cases for lasers and for RF weapons. They need to get trained up to understand where the real risks are, where maybe the risks aren't as much as what they are concerned for. So the infrastructure to do that, the implementation of it, allies and partners. That's been called out repeatedly, year after year in our national defense strategies, in our S&T strategies. We take that very seriously in directed energy. There's a laundry list here of acronym soup. I'm not going to go through all of them, but basically, I personally at the OSD level, under Ms. Shu's guidance as the Undersecretary, am interacting with multiple countries through working groups, trying to figure out where it is we can best help each other to cooperate from a technology standpoint or from an implementation standpoint, without necessarily having to share intellectual property between various vendors or companies in our countries. But very active engagement with allies and partners across the usual suspects that you would expect, both our closest allies and other folks that are relevant for the various areas of conflict in the world. Test and evaluation in the lower right. As a new capability for directed energy, we are going to have to prove some things. The communities that have been around a long time in the conventional world, in kinetics and missiles, people hit the I believe button that a missile will fly out and beat another missile. And so for the most part, there's a way to avoid cost in the testing and evaluation of conventional systems. But nobody is going to believe us in the near term when we say, trust us, we ran a model and the direct energy system is going to work. So we really have a premium in the next, I'd say, near term 5 to 10 years to not just employ these systems for operational experimentation, but for also testing those systems in our CONUS, continental United States test ranges, to build that confidence for the warfighter and to benchmark our models such that fast forward 10, 20 years, we can build lasers, we can say, look, the models tell us it's going to work, and there will be a existence proof that that's in fact the case. So test and evaluation is critical for us to gain confidence in from our customer base, basically. And my last get off the stage comment is on the industrial base, which should be a good lead-in for the discussion of the study. Critical that we understand the industrial base and the supply chains. My vision for the future for our community is that we're going to articulate to that industrial base a consistent demand signal. This is a vision. This is not today, but that demand signal looks a lot like we've made decisions for acquisition programs where vendors can understand the pace of delivery, the scale of delivery, the numbers of systems. We do not do that today. We have one-off procurements, maybe few-off procurements for these experimentation systems. But in the meantime, while we get to the point where we can make those decisions that provide consistent demand signal, we still need to be investing in the industrial base. And there are activities, I'm not going to go through those today, but there are moderately significant investments happening in some certain parts of the critical technologies and the subcomponents and subsystems of these weapons through kind of standard manufacturing technology investment programs in the Department of Defense. So that is happening, but this supply chain study, I think, is really going to stimulate additional engagement for those topic areas as well. So I think I'll stop here and take whatever questions that you might have. Thank you.
Okay. We've got one from the online audience. This is from Sydney Friedberg from Breaking Defense. The question is, what are the critical hurdles to overcome versus cruise, ballistic, and hypersonic targets? Is it simply a matter of power generation or more complex, for example, beam direction, software, or adaptive optics?
I think the short answer is yes to all of that, and I'll draw that a little bit more. For those who don't, in the audience who maybe don't live the dream of understanding all those terminologies, cruise missiles are typically going to operate in subsonic, below speed of sound, to maybe slightly supersonic, with relatively known trajectories coming into a target. And in that instance, for us, in the near term, that's our first low-hanging fruit in the next step of our roadmap. And to get there, we need primarily more power in our continuous wave laser systems and slightly better beam control than we have today. If we can get those lined up in the next few years, then I think we're going to have initial capabilities against cruise missiles, particularly for area defense where you get opportunities to take side shots as opposed to head-on. But as you go to the supersonic and the ballistic and the hypersonic, as it sounds, they're getting faster and faster, but they're also getting more maneuverable and more unpredictable. And so in addition to the fact that we need more capability out of the weapon itself, that's going to start putting a premium on the initial identification of those threats, and that's sensors on the battlefield, whether it's ships or for the Army bases. Do you know what's coming towards you? Do you know when it's going to come in? How are you going to layer your various defensive systems to take on that threat and other threats? So it will quickly become more than just about the weapon. It'll become about the command and control integration and the weapon coordination and assignment that has to come along with that sort of fight.
So that's actually a good lead into another question, which is, this is from John Harper. What are the biggest challenges related to C2 integration?
Great question. So we have a new way of fighting. We have a new way of engaging targets with direct energy. Lasers and microwaves are slightly different. We don't talk about microwaves so much. There's different classification hurdles. But so we need to have a command and control capability, not to prescribe how the services would implement the C2, but somewhere in their command and control, they need to understand, well, what would the direct energy system do against this target? So now you have to know which target it is, or at least roughly the class, if not the actual specific type. Do we have understanding of lethality against that target? If we don't, can we make some assumptions given similar characteristics? Do we have a timeline for engagement for the kill chain that makes sense? And all of that has to be built into the combat system such that it can make those trade-offs against other weapons that it might have available to bring to bear on a target. So I would say, one of the biggest challenges is simply that early part of the decision making in that counter kill chain. What is the target? Where is it going? When is it going to get there? do I have game against that target? And do I make sense today to be the shooter with direct energy, or should I defer to something else in the layered defense?
Thank you, sir. Sinclair Harris, LMI. In a world of continuing resolutions, is that impacting our ability to start new programs to advance these emerging technologies? Does Congress understand their role and their responsibility in terms of keeping up or keeping ahead of our competitors?
That is a great question, and I will not answer it. Continuing resolutions are obviously challenging all around. Congress has to do what Congress has to do. We adapt as necessary. Some cases, programs by programs, but we find a way to adapt to that. So I won't speak to does Congress know. We certainly know that it has an impact on us, but it's hard to articulate that in a broadly worded way.
So coming from the online audience, this is anonymous. Dr. LaPlante suggests the need for DoD to produce CUAS at scale like 155s, yet many programs are stuck in prototypes. Which systems or DE technology do you see as most mature to produce at scale for today's global drone threat?
Well, I think you'll see it in the rollout. There's a list of platforms and programs that the services have been pursuing, the Army in particular. And I'm not here to say the Army is going to save the world, but the Army has put a lot of effort into prototyping direct energy systems for counter-UAS. They've fielded some systems. They have other systems that are in the pipeline for experimentation. Clearly, there's going to be some opportunities to make some decisions when the Army's comfortable about direct energy for counter-UAS.
Okay, this is from Tim Whalen. ETI's report discusses the manufacturing base and its workforce. What are your top concerns, if any, for the federal workforce in managing directed energy weapon development?
So that kind of breaks into two pieces, and I think it's captured in the report pretty well. There's the ubiquitous STEM problem, and we've had many meetings with industry where direct energy is not unique from that standpoint. We need a stronger technical workforce across the board, regardless of which type of weapon you're interested in. Uniquely for directed energy, some of our workforce challenges are going to be very specific niche parts of the technology space. The beam directors for laser weapons aren't necessarily that common to other types of capabilities we would already have in our technical workforce. So that's the first part. But I think the second part is in the world that we're heading towards, where we start having acquisition of these kinds of programs, the vendors that are going to start bringing those capabilities forward do need oversight. They need smart oversight. And so we will have a transitional period I think we're going to have to address, in which we've had science-y government folks in the workforce monitoring science-y efforts from the vendors, and we're going to need acquisition technology experts to oversee the acquisition side of the vendor space as they come forward. So that's a challenge for us, because we don't have the acquisition workforce today that are deeply knowledgeable about our technologies. That's got to come forward. All right. I think that's my get off the stage. I'm going to hand it back to Dr. Serafin. Thank you, sir.
Thanks very much. Well, thank you, Dr. Peterkin, for that great presentation and your skill of both answering and avoiding questions as appropriate. So Dr. Peterkin promised that I would give you all the details of the report. I, as an executive, will delegate that duty to somebody else. I'd like to next hear from Rebecca Wastenberg, who is the lead author and study director for this effort. Rebecca and her team have put in countless hours over basically the last year, putting together the working groups with NDI members and government experts, culling all of that information, technical and policy information, and putting out the report that we're all here to discuss. And so I'd like to bring Rebecca up on stage to give an overview of the key findings of the report and our recommendations.
All right. right, good afternoon, everyone. As Arun said, my name is Rebecca Wastenberg, and I'm the chair of the Supply Chain Study and the lead author of the Directed Energy Supply Chain Study. It's a privilege to be here today to share the key findings and recommendations from ETI's second report in the supply chain series, entitled Directed Energy Weapons Supply Chains, Securing the Path to the Future. Before I begin, I would like to thank a few people in particular. First, I would like to thank the University of Maryland Supply Chain Management Center team for their partnership, especially in the early stages of this study. Next, I would like to thank our interviewees and working group participants, many of whom are in the audience today. I would also like to thank the distinguished members of our peer review committee and our external reviewers for their contributions. I would like to especially thank Mark Neese of the Directed Energy Professionals Society for his partnership throughout the study. And finally, I'd like to thank my fellow authors of the report, Wilson Miles and Jordan Chase, and the entire ETI and NDIA teams, both past and present. As Arun mentioned in his opening remarks, when ETI was first stood up in 2021, we looked across the defense emerging tech policy landscape for where we could have the biggest impact. At the time, we were coming out of COVID, and the pandemic had really laid bare the tremendous challenges that U.S. supply chains faced across nearly every sector. And a lot of efforts were underway to try and address these challenges. We saw this plethora of efforts as a good thing. It was indicative of the issue's importance. However, as we looked across these efforts, we noticed that outside of government, there are very few organizations that were conducting forward-focused work on defense emerging technology supply chains. No one was looking at the specific technologies that are important to national defense, putting themselves 5, 10, 15 years in the future and asking what supply chains need to be in place to support deploying these weapons at scale. That's exactly what our study set out to accomplish. We launched the effort with two specific goals in mind. Number one, assess the state of defense emerging technology supply chains, and two, provide actionable policy recommendations for their development, health, and resilience. We decided early on to conduct the study at the unclassified, publicly releasable level in order to reach the widest audience possible, including international partners and allies, and companies that may not necessarily be part of the traditional defense industrial base, but still have a tremendous role to play. We decided to focus on hypersonics first, launched that report last year, and then focus on directed energy, both high-energy lasers and high-powered microwaves. Our study focuses on 4 aspects of the supply chain: critical raw materials and goods, manufacturing base and workforce, supply chain security and vulnerabilities, and international partnerships and allied nearshoring. We then set up a methodology that really leverages the expertise, especially of our NDIA member companies, those who are living these supply chain challenges day in and day out. So we first partnered with one of NDIA's academic members, the University of Maryland, where we worked with a team of professors and graduate students in their supply chain management center. And they really helped conduct kind of the foundational research to identify key companies, sources of raw materials, and potential vulnerabilities. Like I mentioned earlier, we worked very closely with Mark Neese of the Directed Energy Professionals Society to also help identify those key companies and to draw on his technical expertise. From there, we conducted a series of working groups and interviews with key stakeholders from industry, government, and academia. The key takeaways from those working groups and interviews were compiled with UMD's research and internal research into a draft report, which was then submitted to a peer review committee and a group of external reviewers to ensure technical accuracy before the report was published. As I mentioned, we decided early on to focus on both high-energy lasers and high-powered microwaves as some of the most relevant technologies for DoD purposes. So now for the study and the key findings. Overall, we assess that the current directed energy weapon supply chains for both high-energy lasers and high-powered microwaves are insufficient for fielding the weapons at scale. Why is this? If you look at the history of directed energy weapons, it's not a new technology. It's something the U.S. has been working on for decades. However, there hasn't been a clear, consistent demand signal from government, along with that clear strategic vision for the weapons themselves. As such, current supply chains, including critical raw materials, the manufacturing base and workforce, and testing infrastructure, are incapable of supporting the deployment at scale. They're currently able to produce small quantities of systems with long lead times. Without that clear and sustained demand signal from DoD, and therefore a return on investment, industry is hesitant to make the investments necessary to have secure, healthy, and resilient supply chains. While addressing these vulnerabilities is a formidable task, it is not insurmountable. To fortify directed energy supply chains and fulfill the potential of these cutting-edge technologies, a series of concrete steps by government, industry, and academia is necessary. As I mentioned earlier, the first aspect of directed energy supply chains that we focused on was critical raw materials and goods. For this aspect, we examined the raw materials for high-energy lasers, then for high-powered microwaves, and then looked at some of the overlapping components between the two. While the full report covers numerous raw materials, I'd like to focus on three in particular today: rare earth elements, gallium, and germanium. It goes without saying that these materials obviously have numerous applications outside of directed energy in the commercial space and elsewhere in the defense realm, but they're also critical to directed energy. Rare earth elements have numerous applications in directed energy weapons, but in particular are used as doping materials for the gain mediums, which amplify light in high-energy lasers. According to USGS data, Chinese exports of refined rare earth metals account for 74% of U.S. rare earth imports between 2018 and 2021. China not only mines the minerals, but also controls more than 85% of the world's processing capacity. As such, rare earth elements are a tremendous vulnerability in directed energy supply chains. That being said, there have been some positive developments in the U.S. in recent years to try and address this issue. MP Materials, the only domestic rare earth elements miner, announced first refined production from their newly commissioned rare earth separation plant in Mountain Pass, California. The plant has received partial funding from DPA Title III and has the benefit of allowing MP Materials to produce separated and refined rare earth oxides without shipping the material to China as they had to previously. Another recent development was an award to EVAC Magnetics to establish a domestic rare earth permanent magnet manufacturing capability. Specialized magnets are a critical component of numerous military systems, including high-power microwaves. Again, China currently dominates production of these magnets. A third and final development is that an Australian rare earth miner and processor, Lynas, recently signed an updated $258 million contract with DoD to establish a rare earth separation capacity in Texas. The next critical raw material I'd like to discuss is gallium. Gallium has numerous commercial and military applications, but is commonly used in the construction of semiconductor lasers, also known as diode lasers. On the HPM side, solid-state microwave emitters for HPMs also are most commonly made out of gallium nitride. Gallium is another area where the U.S. is reliant on China, currently importing 53% of gallium from China. Overall, China also controls 98% of the global gallium market. And as many of you may remember, last summer, China announced export controls on gallium that began August 1st, 2023. When the announcement first came out, the price of gallium jumped 20% in the US and Europe, and ever since there's been significant speculation on what the repercussions will be in the long term. Some of our interviewees expressed concern about being able to source gallium due to controls, while others said the announcement was concerning, but they still felt confident they could source gallium as long as they could plan far enough in advance. There is the possibility that in the long term, the export controls could actually spur other countries to restart or begin domestic production of gallium. And because Chinese dominance in this market is actually relatively recent, prior to 2010, Germany, Canada, and Ukraine all produced similar quantities of gallium to China. Another long-term result of the export controls could be that it could act as an incentive, unfortunately, for manufacturers requiring materials to move their manufacturing to China. And unfortunately, there's precedent for this, as happened in following the 2010 Chinese rare earth export restrictions. Only time will tell the impacts in the long term. Given these challenges, we recommend in our report that the Department of Defense, working with Congress, should add gallium to the National Defense Stockpile. While this is only a short-term solution, it's a step that DoD and Congress could take today to bolster defense readiness and help secure directed energy supply chains for the future. The third and final critical raw material I'd like to discuss is germanium. Germanium is one of the primary materials used in infrared optics. Again, this material is primarily sourced from China. As of 2023, 54% of imported germanium comes from China. Similar to gallium, the Chinese government announced export controls on germanium last summer. It's worth noting that the U.S. does keep a reserve of germanium in the National Defense Stockpile, but that's only meant to provide resources in the event of a national emergency. Given the vulnerability of gallium in the directed energy supply chain, we recommend that industry, in collaboration with academia, as well as federal, state, and local government, should take steps to build a domestic gallium nitride production capability. Now I would like to turn to the second area of the directed energy weapons supply chains we focus on in the report, and that's manufacturing base, workforce, and testing infrastructure. Here we see a similar story to the one we told in our hypersonics report. As I mentioned before, directed energy weapons are nothing new. The U.S. has been working on this technology for decades. However, there are currently no directed energy weapon programs of record, and DoD's history of DE funding has fluctuated over time. Due to this lack of clear, consistent demand signal, the directed energy weapon manufacturing base is only able to produce small numbers of systems with long lead times. I'd like to walk through some of the most pressing challenges that will likely present themselves if DoD does begin to field directed energy weapon systems at scale in the future. The first area highlighted by working group participants and interviewees was mirrors and lenses. The challenge here has to do with the current manufacturing processes, which require highly precise grinding and polishing to meet specific tolerances and specifications, sometimes resulting in lead times of 12 to 18 months. There's also a shortage of specialized manufacturing facilities with the necessary equipment and expertise, which can limit production capacity as well. Due to the critical nature of these mirrors and highly complex manufacturing processes, any supply chain delays earlier in the process can have cascading effects on the entire production schedule and deployment timelines. Next is power supply, specifically when it comes to batteries. China currently dominates the international battery market, and domestic manufacturers are unable to compete with the lower-priced Chinese commercial lithium-ion batteries. Because of this, interviewees stated that most directed energy weapons and many DoD systems in general buy commercially sourced batteries from China. Similar to semiconductors, DoD comprises an extremely small piece of a largely commercial battery market, and directed energy weapons are an even smaller slice of the market. While there's been discussion in recent years about domestically sourcing batteries, including the acknowledgement that battery reliance on China could be reduced or eliminated, customers have yet to express a willingness to pay the higher cost associated with domestic sourcing. Battery supply is an area where different parts of DoD, including DIU, ANS Industrial Base Policy, the services, and other parts of the interagency, especially the Department of Energy, are focusing a lot of time and attention, which bodes well for directed energy. Another manufacturing-based challenge for directed energy weapons is the lack of standardization across directed energy systems. This lack often makes it difficult for industry to see a return on investment due to very small production runs that are often highly specific to individual systems. Simply put, certain components are critical to a system's effectiveness, but are necessary only in small numbers and require a highly specialized process. As such, this leads to higher unit cost and manufacturing challenges. This is especially true for coatings, according to multiple working group participants. To date, production of coatings has been largely heterogeneous, with many diverse and proprietary approaches to coating formulas. Because of this, there has been little standardization or consensus on preferred coating materials in order to build robust supply chains. Additionally, because of intellectual property concerns, system integrators often have little visibility into the specific coating materials used by their subcontractors, resulting in potential lack of awareness of supply chain vulnerabilities. This lack of standardization is another area where the Department of Defense has begun to take note and is trying to work with industry to standardize where possible. In December 2022, OUSD-R&E published a Directed Energy Weapons System Modular Open System Approach Reference Architecture in response to congressional and DoD service leadership mandates for the use of MOSA. This is an important step in MOSA for directed energy, but now it needs to be implemented. Testing infrastructure for directed energy weapons was a key issue raised time and again by interviewees and working group participants. Obviously, a detailed analysis of directed energy testing infrastructure could be the subject of its own study, but we highlight some key issues that were raised by working group participants. A common theme we heard was the lack of directed energy testing capabilities. The actual number of testing facilities is not so much the central concern, but instead it's the testing regulations, especially the FAA regulations, which play a far more substantial role. Since most directed energy weapons in development are meant for integrated air and missile defense, a majority of DE testing requires a discharge of high-powered energy into the air. This requirement leads to significant challenges due to heavy restrictions on testing above the horizon in order to safeguard air and space assets from potential damage. Finally, in this section, we looked at the workforce necessary for directed energy. A few specific challenges were raised by working group participants. First, coatings, given the significant expertise necessary to construct and apply these coatings. Industry participants often refer to coating construction and application as an art form and something that takes extensive time and skill to master, presenting a potential workforce vulnerability if demand were to rapidly expand. While there's a significant coatings workforce in the US, there's only a small number of professionals devoted to the defense industry. According to interviewees, if demand were to rapidly expand, there would likely be difficulties in finding reputable coders with reasonable lead times and pricing. Finally, optics, where optomechanical engineers are responsible for the design and integration of optical systems, play a pivotal role. These engineers bridge the gap between theoretical optics and practical applications, ensuring optical systems function optimally in real-world scenarios. According to some of our interviewees, there are only a handful of schools, both 2-year and 4-year, with optics programs in the US, which leads to a limited supply of optics graduates. Given these challenges, there has been some work to help address them. We outline a plethora of different public-private partnerships in the report where industry, government, and academia are coming together to address some of these challenges. Given all the challenges in the manufacturing base, testing infrastructure, and workforce, we make a number of policy recommendations in our report. The most important and critical step the DoD should take immediately is to provide a clear, consistent demand signal to industry by designating appropriate high-energy laser and high-power microwave systems as programs of record to send that extended demand signal. This will allow industry to begin investing and help secure directed energy supply chains for the future. On the testing side, DoD should designate more existing testing sites as special use ranges in order to permit expanded testing of directed energy. And finally, DoD should establish a directed energy university consortium with the clearly defined goal of creating a strong workforce to meet future directed energy needs. The third aspect of directed energy supply chains we focused on was supply chain security and vulnerabilities. Here we analyzed a number of different issues, but in particular, we focused on analyzing the financial health of companies within the directed energy industrial base. We partnered with an NDI member company called Rapid Ratings and to analyze the overall financial health of a sample of companies. And overall, we found that generally directed energy weapons companies were doing fairly well in comparison to other similar companies. However, there are still a small section that are in the high-risk category. As such, we recommend that further analysis be conducted. There are serious issues with limited suppliers within the directed energy supply chains. And as such, even a single company failing could have catastrophic effects throughout the supply chain. The fourth and final aspect of DE's supply chains we examined was international partnerships and allied nearshoring. Overall, we identified a few key areas where international collaboration could strengthen DE's supply chains. First, the U.S. should look to Australia, Canada, and Japan to help diversify supply of critical raw materials and goods. The U.S. should also look to the United Kingdom to help with sourcing beam control components, as this is an area where the UK has particular expertise and a well-established industry. Finally, given DE testing limitations domestically, the U.S. should look to partners and allies to help increase the directed energy testing up-tempo. Despite these opportunities, several challenges must be overcome, including export controls, classification challenges, and intellectual property challenges, just to name a few. In conclusion, directed energy weapons supply chains face numerous challenges and vulnerabilities currently. Many of the critical raw materials are sourced from China. The manufacturing base is only able to produce small numbers of systems with long lead times. Domestic testing infrastructure faces tremendous regulatory challenges, and the workforce is small and faces shortages. The supply chains have multiple instances of limited, single, and/or sole source suppliers, and international partnerships face challenges from export controls and overclassification. That being said, in select areas, the U.S. government has taken note, and is beginning to take small steps in the right direction, whether that be through grants to domestic refiners of rare earth elements or other such activities. However, much more work remains if the U.S. is going to have strong, healthy, resilient directed energy supply chains in the future. Thank you, and with that, I'd like to turn it back over to Arun.
Thanks, Rebecca, for that great presentation. I'd like to now invite our panelists to take their seats at the front of the room. It's my honor to introduce, as he approaches the front of the room, our moderator for today's panel, Mark Neese, the Director Emeritus of the Directed Energy Professional Society. Rebecca's thanked Mark and sung his praises. I will repeat such now. Mark's niece is twice retired from the federal government. He spent 37 years in the military and civilian service, apparently in the Air Force, I understand, including time as a pilot with over 7,000 flying hours. He's also formerly the director of the High Energy Laser Joint Technology Office, which is the forerunner of today's Joint Directed Energy Transition Office. He was also the chief of the laser division at the Air Force Research Lab. With that, thanks, Mark, for all your help with the study and for moderating the panel today.
Well, thank you, Arun, and it's a pleasure to be here today and to help kick this study off. It's a long time in work. I will echo what was said before. Rebecca, Wilson, Jordan, you guys did a bang-up job, and it's good to see Sam in the audience as well, who was the initiator of this. I'm pleased to welcome a robust panel that's going to talk on the industry and government perspectives on the directed energy weapons supply chain. So introducing from left to right, Mr. John Jewell from the EPRIS system. EPRIS develops high-power microwave capabilities for us. John serves as the Vice President of Operations at EPRIS. He joined EPRIS in 2020 as the Director of Manufacturing, brings over 2 decades of aerospace and defense industry experience, spanning operations management, strategic manufacturing planning, and cross-functional project management. Prior to EPRIS, John spent 17 years at Raytheon and in a variety of operations, manufacturing, and program leadership roles. To his right is Tyler Griffin, Lockheed Martin Company, developer of high-energy laser systems. Tyler is the Lockheed Martin Strategy and Business Development Director for Mission Systems and Weapons Market Segment. In this role, he's responsible for ensuring LM's products and mission capabilities remain ahead of ready in the areas of avionics, aircraft modernization, launch systems, and high-energy laser weapon systems. And completing the panel today is Mr. Chris Berry from OUSD A&S. I'll describe that. He's the principal engineer for directed energy weapons to the Director for Electronic Warfare, the Office of Undersecretary of Defense for Acquisition and Sustainment. In this capacity, he works directly with the Principal Director for Directed Energy, Dr. Peterkin, who spoke to us earlier, OUSD R&E, to maintain visibility across the undersecretariats. Mr. Berry has been working in directed energy for over 20 years, working across multiple OSD and Navy programs. I'll give each of you a couple of minutes to provide some opening remarks. John?
Thank you, Mark. Really appreciate the introduction of this great panel. I also like to say thank you for hosting the event, and Rebecca, thank you for putting together such an amazing report and doing all the hard work to gather the business intelligence to piece together the information you just shared. It's very well put together. Excited to be here to talk about it today. I won't go too much into the background. You did a great job, Mark, of introducing the career I've had in defense technology, but it's very important. I'm very passionate about it. And the reason why I went to EPRIS was to bring speed to what we do today, and how do we bring forward these great technologies like high power microwave that are needed to go solve emerging threats like counter-US counter-swarm threats that are there today. And EPRIS has done just that in a short amount of time, 5 years, just over 5 years. The company's been alive. We've iterated on 4 different systems. We've done that using like an agile, lean startup methodology. And those 4 generations of systems. 4 systems are now being delivered to the Army. They're one of the ones that were highlighted in the report. It's actually one of the 28 programs that are highlighted on between page 10 and 13 that are in the early adoption phase, and we're really excited about where we are. One thing that we did great on that one, early or on time, is not typically spoken a lot on programs in the DoD. We did that. We are early, we're on time to deliver these systems, we're ready to go, and we're continuing to mature and reduce risk in our industrial base to support more orders of high-power microwave systems. So thank you.
Thank you, John. Tyler?
Thank you, Mark, and I'd like to thank NDIA and the Emerging Technologies Institute for the great work and collaboration driven across the supply base. I'm representing Lockheed Martin, and very honored to be speaking on behalf of all the great and intelligent men and women that represent the laser weapon system supply chain, and we'll look at this precipice of transformational change that laser weapons are approaching. And as Dr. Peterkin laid out, there are clear hurdles to overcome to transition, but we are on the precipice of that transition together, and it's outputs like this study that help give us the guideposts to inform how we as an industrial base can come forward and realize something that doesn't come along very often in one's career. When you think of transformational change, I'll think of Admiral Rickover's Nautilus and pushing the nuclear navy and doing so in 3 years' time for that first prototype. We're facing similar challenges in how we do something new. It's anything but easy to talk about introducing to the battlefield a 21st century strategic deterrent that can move at the speed of light and partner with other instantiated effectors to deliver an overwhelming and enduring advantage for our forces and our allies. And that is what motivates us. That's the caffeine in our coffee, if you will, to drive forward and help realize that transformational change. The laser was invented more than 60 years ago. Lockheed Martin has been working for, as Rebecca noted, many, many decades, more than 40 years, 4 of them to be exact, on how to realize this capability. But as we'll get into the supply chain discussions, our world is really at the bottom of the periodic table. Those difficult to pronounce and not often studied elements that help realize robust solid-state electric laser capability that provides many advantages, many of which Dr. Peterkin summarized. But I want to emphasize a deep magazine, a transformational change of a nuclear navy, the ability to not go into port or be burdened by supply ships to bring the fuel. A deep magazine that laser weapons can provide is now partnering and allowing our forces to stay in the fight longer and allowing those proven and hardened kinetic defectors for more challenging or stressing threats. And that emergence is something that has to be earned. And why? Even though it was more than 60 years ago the laser was invented, and the Pentagon has probably wanted that capability for more than 60 years, why is it not there yet? Well, we have to drive affordability, we have to drive reliability, and it has to be a mission use case that has been earned by the industrial base. So from a Lockheed Martin perspective, from a laser weapon system industrial base perspective, we're driving to realize the potential of these capabilities and look forward to the discussion here today. Thank you.
Chris?
Thank you, Mark. I want to round out the thank yous to NDIA for inviting us here to be on the panel here, and an excellent report that you put together. I think it definitely echoes a lot of my thoughts as well, and we'll probably be touching on as we move forward. Mark mentioned I'm currently at OSD Acquisition Sustainment on the Electronic Warfare Shop, where I'm actually starting to get after one of the problems that Dr. Peterkin talked about in his questions. How do we educate our acquisition workforce in the technology that is directed energy? So I've been in that office for a little while, trying to prepare them for the first programs of record to come along so they can provide that oversight that they need to provide. That's set against the backdrop of what I've seen over the last decade. Just to quantify a little bit, I sat down this morning with a pad of paper and tallied about 30 different DE programs that I can count that have come together in the last 10 years. 24 of those have been put in the hands of the warfighter, where we've gained valuable feedback that we can drive back into the design. And they've gained understanding of how this technology works, maybe a little bit differently than what they've read in their science fiction books. So that's over the last 10 years, but you can understand that that's been a pretty steep incline in the last 5 years. Match that against the fact that over the last 5 years, we've also seen a trend of both industry, IRAD, and government procurements working not in onesie-twosies like we were in the past, but in procuring 2, 3, 4, 5 systems at a time. That's been a real test of our supply chain. And on a program-by-program basis, we see that result in extended lead times and difficulties in meeting schedule. And I think that just highlights the importance of what we're doing here today, is to look for solutions to prevent that in the future as that ramp rate continues to go up into these programs of record where perhaps we're procuring tens of units in a given year. which will be certainly a challenge to our current supply chain.
Thank you, Chris, and that's a great lead-in to the first question I've got for the panel members. How has the directed energy weapons industry evolved over the past few years, and what are the challenges and opportunities in the current supply chain landscape? We'll work our way down. John?
Well, EPR's only been around for 5 years, but in that short amount of time, there's been a lot of evolution in high power microwave capability. And if you think back into the start of GaN being inserted into semiconductors, really enabled what we do today. And there's more happening right now to develop the next power levels and other frequency band capabilities for us. So it's evolving very quickly. There's been a lot more interest. I mean, reports like this bringing to example some of the importance of programs that are out there. There's clearly a lot happening. I think you said 30 or so programs. I think the report had around that number as well. Heavily focused on high energy lasers, and we're catching up a little bit on the high power microwave side. I think it was about 7 of the 28 programs listed in the report were high power microwave focused. So definitely want to catch up a little bit there and make sure that we're evolving at the speed of the threat and of the need. So.
Tyler?
Yeah, thank you, Mark. And I'd say if we look back 15 years, the industrial base has responded to a sine wave of demand signals and prototypes. And I would say in each of those cases, the amplitude of the wave is growing. We're maybe not at the activation energy necessary for production at scale, but what is happening over the past 2 to 3 years, some of the opportunities are the operationalization, the lessons learned, not just for the material and how to build these systems, but also how to employ them across the full .mil PF spectrum. And it's how do we leverage the doctrine, the leadership. We won't spell out all of the elements, but how do we bring this forward to have an enduring capability? And I look at the past few years as informing the arsenal of democracy. And the laser weapon system supply base is now at that point where we're finding the applications and the missions, counter UAS being one we alluded to, and the Army making great progress there, the Air Force as well for some of their rapid demonstrations. But I look at the U.S. Navy, and Helios is on the U.S. warship for the life of that warship, and it's not just added, it's integrated into the superstructure, it's integrated into the combat system. And sure, there's more to go. Better integration, more KEDE collaboration can be harnessed and brought forward, and those are some of the opportunities we have going forward, and appreciate the leadership of the government to bring forward things like MOSA, and that open systems approach will help us fuel the drive to get these capabilities to a point where they can earn their way into the arsenal of democracy.
Chris, anything you want to add?
Mostly just to echo, I think what has already been said, right? 10 years ago, we were working in a very serial environment of one unit after another as one program came along and the next program came along. As things have evolved in this current sine wave, we're seeing multiple units having to be procured at the same time. That requires some parallelization of production. We're seeing that pick up in industry in some areas. That's the challenge that we've had. I think the opportunity that I see is that feedback from the warfighter. I think the feedback we were getting in the past, onesie twosie touches here and there, was valuable. Today, the feedback we're getting where we are putting capability not only in the hands of the warfighter but also in real operational environments is feeding back even more rapidly. And we need that data stream to increase if we're going to get these weapons to the peak they can be.
And I'll just add that Tyler brought out a sine wave. And so with the sine wave, there are crests and there are troughs. And part of what we're addressing in this study in the supply chain is a consistent demand signal in there. It's good when we're cresting. It's tough when we're troughing because the industrial base reacts to those troughs as well. And so I think echoing what was in the report on supply chain consistency and kind of leveling out some of those troughs and valleys can be useful. All right, for my industry partners, the next question From an industry standpoint, what innovations and/or advancements are critical for improving the health and resilience of the DEW supply chain? Tyler?
Sure, Mark. I think from an advancement perspective, how to enter an already existing and robust DoD capability and the 21st century security that's being provided today, how we bring directed energy technology into a very kinetic world. And John and I will work on what the operations analysis needs to be, what the command and control needs to be, to create that layered defensive architecture, and one that is well known, and it plays into the training element of .mil PF. How do we inform and educate what the soldiers, many of whom could be in school today, will naturally come by in terms of how they will employ these immense and game-changing capabilities, but how do they do them in partnership with existing capabilities? That's a big advancement that, as these systems are robust and reliable, we'll then be asking those questions of how do we advance the command and control, say, in an operational theater or higher echelons of battle management. That integration piece is a big challenge we'll need to work through to transition at scale.
John?
I agree 100% with that. I mean, if you take it from a system of systems architecture view, like an OB1 architecture view, there's space for all of these effectors in that system of systems view. And what would do harm to us is if we look at very myopically as like individual companies or individual performers of product deliverables, and if we can expand that out, look at it more of a system architecture, I think we all will win. If we look at it that way. I think from a more advancements on the tactical perspective, I think emphasizing what was put in the report on testing infrastructure in the U.S. is really important. We have a lot of headwinds against doing open air testing for both lasers and hyper microwave systems, so that advancement needs to happen. The adoption, the understanding of the safety elements that we can put in place, the mechanical safety locks we can put in place, or the training for folks to feel safe using and testing these systems at existing test ranges. I'm not advocating you need more test ranges. I think we need more right away at the ranges to get us to enable us to do what we need to do.
All right, thank you. Wilson, do we have one from the online audience?
We got a couple. So this is from Sydney Friedberg from Breaking Defense. So great overview, but this doesn't boil down to, quote, DoD needs to spend a lot more on DE so industry knows it can get a return on investment. When Peterkin just told us there's a lot more to figure out than the technology. And DE isn't quite ready to scale up, even for CUS. So I think, can you kind of go into a little bit more about the balance between technology development and that demand signal?
You want to tackle that one, Tyler?
Yeah, absolutely. And I'll pick up on John's good point about test and evaluation. And the Office of Naval Research in February of 2022 demonstrated what these systems can do at the Army's Energy Laser Test Facility at White Sands, New Mexico, negating not one but two Sergei cruise missiles. And that shows where the technology is, but that's one testament. And now we have to talk about how do we spread that knowledge and that's gained. And I'll be honest, from a community writ large, industry and government, when we go into a test, we've necked down from the acquisition professionals, the industry leads, those who led the design, and those test results, some of which are extremely compelling, as the Office of Naval Research achieved in February of 2022. But now it's how do we drive those lessons learned across the community? How do we avoid proprietary or, say, trade secret stovepipes so that that knowledge can proliferate and we can showcase these examples which clearly have warfighting capability? How do we showcase their ability to transition at scale? That becomes a big hurdle for us going forward.
Yeah.
John?
I would say there's definitely proven ways to reduce lead time and accelerate production, and it does go back to having good intelligence from the consumers of what you're going to buy. It's proven in consumer electronics, automobile manufacturing. We make educated bets. They make educated bets on how many are going to sell, right? Having that understanding from the acquisition community of how many do you think you're going to buy and when will educate the industry performers to go make smart investments in capabilities, test facilities, or manufacturing facilities, and work with our supply base. They're ready to go, by the way. Our suppliers are all wanting to help. They're very patriotic in this way. They want to help. They know we have a problem. They want to help. We just need to be informed with that information to go flow that through the investment chain and make smart decisions as industry leaders. So,
Chris, anything to add?
I think as far as being able to get after the current threats and then continue the S&T to be able to get after more advanced threats, if I heard the question properly, is something we can do. We've done on other platforms and other capabilities. The first airport platforms that we deployed were not jets. We got after what was available at that point in time, and we can continue to grow the science and technology development in parallel and transition that to industry to take to scale.
Yeah, in a conversation we had earlier today, I think in particular the counter UAS mission set is an ideal trade space for the DE community. It offers us the opportunity to take out a threat at relatively inexpensive cost. The cost factor can be on our side when we use electrical power to take out those and bring that forward. All right, Wilson?
Yep. So this is from Anonymous, and it's about the UCA. So UCA lacks good government oversight, funding projects with little chance of transition. Texas A&M seems to run it in a vacuum. If this is established for DE, as the report recommends, how can we do better?
I guess I'll take that one on from a standpoint. So there are some challenges with the UCA system as it's been put forward, but I think there are lessons to be learned from that. And so with the recommendation that we put a university consortium in place specific to directed energy, I think that we can garner those lessons learned and really put the emphasis back on in collaboration with some of the recommendations, like establishing, activities within the JDETO that can help focus that activity and keep us on the right path to do that. Not to say that the UCA system is bad. There are certainly opportunities, and it enhances our overall industrial base to create that basic research at the university level, because that's where we're developing the workforce for the future. The people that come in and work in the directed energy community come from that workforce. They come from those research activities, and so there's good to be garnered from all of that activity, but let's keep it focused and make certain that it's meeting the needs of what we're looking for from both an industry and a government standpoint. Hope that answered it. All right, I got another one here. This one's going to be directed to Chris. Are there specific government initiatives or incentives to encourage innovation and investment in the DEW supply chain?
So innovation and investment, I think there are. I think you spoke to it a moment ago. Dr. Peterkin spoke to it. And a lot of the investment is going in through the currently JDETO environment. I think we also have efforts under IBAS funding. I think Frank referred to that is working through some direction from DepSecDef through DMAG and also Mantech efforts. So there's absolutely effort going into that, targeted a lot of the areas that we see in the report, optics, optical coatings, specific areas that are hard for industry to get after. We need to grow with a little bit of help from the government.
Okay. Do we have any questions from the in-house audience right now? Wilson, I'll come back to you then and see. I'm guessing we got at least one or two more from the online audience.
Yeah, so this is from Meredith Roten. So directed energy weapons have some limitations related to use in inclement weather like fog and rain. How close is the military to finding ways around these limitations?
Chris, you want to hit that one?
Well, I mean, physics is going to limit any weapon to some extent at some point in time. There's going to be something that blocks the capability. So we are taking it as far into that realm as we can. I think earlier we talked about adaptive optics that helped us overcome some weather environments. High power microwaves has far less restrictions in those higher humidity environments than maybe high energy lasers. And then ConOps plays into that a little bit as well. How do you optimize your engagement angle if you are in a maybe not the most optimal atmosphere? That also goes back to making sure you understand, and this goes to the C2 question, what is the right weapon for this particular point in time for one particular incoming threat, and making that decision based on a model that understands what you're capable with your kinetic weapons, what you're capable with your non-kinetic weapons, and making the right decision on which one to employ for that particular threat.
John?
Yeah, I think supportive of exactly what Chris said. I think if you could have the best effector in the world, but if you don't have a good C2 that informs it, or you don't have an environment that it can work in, then you will lose. And so I think back to that system architecture, you have to have both. You have to have a complementary HEL, and you need an HPM system that can address the threat at the time you need to.
Tyler?
I'll just add great points as well. I would highlight the different tools that laser weapon systems can bring. And Dr. Peterkin talked about the telescope that comes on board with a laser weapon system, which more often than not can be used in ways that we don't even anticipate. And Helios being on USS Preble, that is something we're learning from. And we're seeing that this multi-band camera system with the ability to focus is providing situational awareness that wasn't necessarily originally thought when we just think of how a laser will perform. And if the laser weapon is not the proven effector, noting that the environment could be challenging for the laser weapon, it's also challenging for the inbound threat. But the laser weapon is still delivering value to that battle space by bringing a novel situational awareness and ISR capability that many times can penetrate through those deleterious environments. So there are added benefits, not just with the layered benefit of an effector, but also the situational awareness and battle damage that can come with it.
And I think I'll add that Dr. Peterkin brought up a valid point in that DE weapons are not the end-all. They are meant to complement our kinetic effectors. There are good days for DEW weapons. There are not good days for DEW weapons based on weather conditions, other activities that are out there. But with the command and control integration, we can allow that command and control to select on the good days where we can use the DEW effectors, and on the not so good days, maybe we have to use a few more of the kinetic effectors to achieve the same results that we're looking for. And so that all builds back into our supply chain. Part of what we can do from a DEW standpoint is relieve some of the pressure on the kinetic effector supply chain by employing these DEW systems in a joint battle space. And you have another one, Wilson, for us.
This is anonymous. What does a real market signal look like? Is it a plan? Is it a speech, a program of record, multi-year contracts? Could you be a little bit more specific?
Tyler, why don't you hit that one first?
Yeah, absolutely. I'd say if we look historically, the laser weapon budget averages $900 million to $1 billion per year. That's spread over academia, industry, federally funded research and development centers, and seeing a change in that, a step change, would be a start. I would also say continuity in budgets. And one great thing the US DoD does is we publish annually where money will go over the next number of years, 5 years if we look at a FIDUP cycle. That certainly helps indicate, and I know there's no ill intent here, but sometimes year over year there are changes in which program or which part of the portfolio is receiving that budget. So I would say twofold is continuity of those budgets and then a steady increase to the aforementioned amount.
I think well said. I would add that it's got to be complementary to Dr. Peterkin's chart on transition enablers. It talks about that crawl, walk, run methodology. The demand has to flow like that. The funding has to flow like that to be consistent and have some continuity. But at a basic level, it's how many and when, right? So how many and when, and then we can start doing some math on what does that mean down the chain to make the right decisions.
This is from Caleb Olmert. What can international partners bring to this challenge? Are there leaders in R&D, better ranges for testing, supply chain contributors, or manufacturing experts that we can partner with?
It's actually a really good one to add to the last question. I forgot to mention that, like, that demand signal should be inclusive of our allied partners, right? We don't want to think that just what do we need domestically. What do we need holistically from our allied partners? So I think that's really important, and having the regulatory body support some of that.
I think Frank answered that well earlier today when he said yes. There are opportunities for international collaboration. There are opportunities for us to explore joint use test ranges across the globe. There are opportunities for us to leverage technology areas where we may not be the industry leader in that tech space, but it gives us the opportunity to work with our partners, to work with our allies, to bring those capabilities forward. So from an international perspective, I think absolutely there are opportunities for us to move forward, and to do that, we have to have some willingness. I think pointed out in the report are some policy changes, particularly as they relate to export control, because it limits some of the dialogues that we can have with our most trusted partners, that we would like to be able to continue those activities and those collaboration efforts with them. Okay, I've got one here. What role does academia play in research and development to enhance DEW technologies, and how can academic institutions foster collaboration with industry and government? I'll let you guys work your way down the line there, John.
I think there's some good examples put in the report for sure. I think there's been other examples of that. EPRS has had a good partnership with Oklahoma University. Some partnership happening around the advancement of testing high-powered microwave systems. So that's been a good partnership, as well as creating ready-to-go work, folks to feed into the workforce, right? And understanding what are some of the new competencies that we need as industrial partners for the engineers or the operations leaders or the scientists that are coming out of academia today. Make sure it's relevant curriculum today that supports what we need and kind of ready to go day one, ready to go employees. So.
And I'll add from a twofold perspective. Firstly, in general, there's a continuity of leadership in academia that can drive through challenges, can realize that a misstep in a lab can be overcome. It may take time, it may take more resources, and I think that ability in the 6-1, 6-2 to really push transformational change and to learn and feedback can be a significant benefit on the academic investment. Secondly, to take that a little deeper, two Lockheed Martin examples. One is more an architecture base, and the fundamental theory of spectral beam combination, one of the electric fiber laser techniques available for propagating a very high quality beam on target to give that lethality at range. MIT Lincoln Labs, amongst others, was a pioneer in that architecture, and it was transitioned to industry, Lockheed Martin being one of them, to employ at scale and productionize those theories and those applications. For that to work, you need a set of precise optics, and Lawrence Livermore National Labs made great progress through the Nuclear Ignition Facility, the NIF, but it wasn't directly applicable to a laser weapon space, and that's where industry and academia were able to partner, and Lockheed Martin was able to go into production with some of those critical optics. So those would be two examples where the academia and the industry partnership has borne fruit as we push towards production at scale.
Great examples. I think some that come to mind for me are the Pulse Power community leverages a few unique university environments across the country, as well as some very high-end optical schools as well. Those are limited, but we partner with them wherever we can. That produces not only the technology that we need to move forward from that 6162 level that starts to push into more applied capabilities, but also the workforce. And I think we need to continue to grow that, similar to what's being asked for in the report. Reach out to other universities and grow that organization.
And I will add that in my role, both at the Joint Directed Energy Transition Office prior to and with the Directed Energy Professional Society, we put a large focus on creating that pipeline of workforce with research grants, grants that are through the Office of Naval Research and the JDETO, allow us to fund internships, activities at our service academies, and create at those pockets, those institutions that have really good research activities that are DE focused, to be able to continue that pipeline, keep the people moving through that system and doing that. And obviously, the recommendations that came out of the report are, how do we expand those roles? How do we increase that? Because producing 12 to 15 folks a year to replace the graybeards in our society is not appropriate. Is not adequate. We need to increase that and see that come forward faster. I think we had one from the audience.
Yes, Chris Gigliotti from Little King Army Depot. There's been a great emphasis on the commercial industry and their participation in the supply chain. Is there room for the organic industrial base to be involved in this? And if so, how do you foresee that being carried out?
You want to speak from an OEM standpoint?
Yeah, and just could you clarify organic industrial base for me?
Sure. The organic industrial base, such as the Little King Army Depot, is the depot for the Army. So we're considered part of the organic industrial base, where we work on the sustainment side of things. So especially through public-private partnerships with Lockheed Martin or intergovernment collaboration.
Yeah, great. Thank you. And I would say there's absolutely a space there in terms of getting over the activation energy to produce at scale. Logistics then play a key part, not just domestically, but globally in terms of how that capability comes forward. And we look at the logistics piece of .mil PF. I see that as another key area where that supply chain and partnership will be key to deploying these systems in line with the National Defense Strategy priorities.
Anything to add, John?
I think, well, so I think the answer is yes. The short answer is yes. There, 100% is, yeah. That's, and I think it's already happening in certain areas.
Yeah. Can you elaborate on the mission sets that HPMs are well suited for?
That one comes to you, John.
Well, I think swarms. I mean, if we were to say one word in answer to that, it's the swarm threat. We've done some initial testing over the course of the last couple of years. Some with the Army RICTO under the indirect fires protection capabilities program we're under, doing some of that effects testing. So it's definitely swarm effects, but as well as single targets as well. and counter electronics. I guess I could add to that. It's bigger than just counter UAS, but counter electronics is another effect area we can have.
This is from Anonymous. Are there commercial applications in directed energy that can help create the market that we need?
Maybe the reverse of that we've taken advantage of where there is nearly alignment with industry. I think we've gained a lot of high energy laser capability out of the automotive, industrial, and the industrial cutting and welding environment, and some of that feeds back in where we can then take our directed energy capabilities and feed them forward. I've seen some attempts to look at not to pun, but deep drilling and mining. There's been some look at that. There's been looks at some other areas such as optical communications, but in general, it's a difficult jump. I think we are typically captured separately from those that align. You can kind of see this in some of the structure that is the research and engineering arm of OUSD, where they've broken off some of those technologies and put them separately and intentionally because they do not have good industry partnership.
Yeah. To add to Chris's points, agree with the drilling market. The demand signal has not necessarily been there. Laser comm is certainly an interesting ancillary space for the underpinning elements of the supply chain, as is power beaming is one area where we're seeing some uptick, both government and commercial, but that demand signal is relatively nascent as well.
I would say we have a slightly enabler part of our system that's around power efficiency that we're entering into some commercial opportunities in relative to power efficiency, less on the high power microwave effect side, but more on the IP we've developed to create the high power microwave capabilities, power efficiencies. We're using that in some commercial areas.
Great. Just for a clarification, 1 question or 1 minute? Okay, great. Okay, so I've got one final question then for the panel. As we end up here, are there successful examples of collaborative efforts that have strengthened the DEW supply chain, and what lessons can be learned from them? Start with you, Chris.
I think there are typically they've been on a program by program basis where you see program offices working directly with the industry partner in the development of a given system, and the beginning of that program starts with a deep look at what that supply chain challenges is and how the program office can help work those risks. It's the kinds of things we're seeing today with the output of this report and also the National Defense Industrial Strategy, the synergy between those two documents that I see that tell me we can now lift this up, maybe work this at a OSD and industry-wide level. And that's I think the promise of what we're seeing today.
Tyler?
I'd say the workforce elements are especially pertinent here from a collaboration perspective. And credit to the Airborne Laser Program. A decade of lack of, say, funding, but that community and the lessons learned live on. And there are lessons learned that sit with graybeards. And that knowledge transfer leads to collaboration within the supply chain because people know who's who. And you want those lessons learned to drive affordability and to mitigate risk. And that's an area where I see barriers or, say, organizational stovepipes being broken to enable the collaboration to deliver a mission capability that earns its way into budgets and future inventories.
John?
A couple of examples already talked about a little bit. Mantech is a good area. I mean, the depths, like creating that forum for not to make you happy or smile, but like that's a really good forum to get people to collaborate and talk and have interchanges. And the depot and the Direct Energy Program Office there helping supporting some of the transition. But we definitely need more of it.
All right, to finish up, we're going to be each of you a couple of minutes to provide some closing thoughts on the strength of our directed energy weapon supply chain. So we'll start with John.
Yeah, I think I want to reflect back to one of the questions that came out from the online audience around what does this mean? What does a demand signal mean? And I think it's really, if you look at every one of the programs that are listed in that page 10 to 13, the really important part of the report, what is the transition plan for every one of those? And then pulling on a statement that Dr. LaPlante said back in an article that was published in December is production matters, right? We aren't in the business of just creating cool technology. We need to get into the business of creating products that are going to go solve problems, and we need to do it at scale and at rate. So taking action and living into that, building on that production matters. Let's get these programs that are supposed to transition into transition states, the ones that are ready to go, get them transitioned, get them into production states, get them funded appropriately to reduce risk, and then continue the development effort in the areas that need more development funding.
Tyler?
Yeah, in closing, 2 quick points. In the opening, I alluded to Admiral Rickover and talked about the Nautilus and the paradigm shift that the father in the nuclear navy was able to drive. A personal story, I once had the opportunity to have dinner with the father of Aegis, Admiral Wayne Meyer, and it was before the naming ceremony of DDG 108, and an honor and a highlight of my career. At a recent Directed Energy Professional Society event, I'll admit I was a little bit lost looking for one of the big symposium lectures, and I came around a corner and was face to face with the bust of Admiral Meyer as the father of Aegis, and his continuity of leadership, Admiral Rickover's continuity of leadership, that determination, that drive, helped to realize a vision that has forever changed the history of those systems. That struck me, seeing that bust of somebody I'd met in person, and I now see a call for whose bust will be made for the transition of laser weapon systems. As we achieve that transformational change, what building will that be in? Who will that be, he or she, that drives the transformative change to bring laser weapons into the field at rate? And I don't know who that is, but secondly, and finally, I do know that whoever it is has a good guidepost with this NDIA study for how to realize that vision and how to make it happen. So I'm very excited for the future and thrilled to be a part of this. Thank you.
Chris?
Maybe just to touch a little bit on how I answered that last question as well, I really do see a lot of synergy between what the industrial base policy group at OSD has come out with and what NDIA has come out with. I think there's a lot of overlap between the 2 reports, structured slightly differently, but the same story is being told by both with different points, which kind of highlights maybe my closing point is that coming into this career field, I remember thinking, this was back in 2000. Funding was primarily going to the Air Force program at the time. So me and the Navy, I saw a little bit here and there come along. And every year we weren't sure what the next program was going to be and how much money we would have. But every year it seems to have grown and grown and grown. At some point, I think it was in the early 2010s, I was wondering if we could sustain this continued growth and every year's going to be a little bit more busy. Apparently we have. Because we're here today again now at the DoD level and all across all of industry level, looking at these problems together and continuing to work together to try to work that. I think that does come a lot from organizations like NDIA, organizations like the Directed Energy Professional Society, organizations like the Joint Directed Energy Transition Office, all working across industry and DoD to make sure that we're talking to each other and working well together.
Thanks. And, I'll add on that it's my belief that the DE industrial base in the United States is ready to answer the challenge put forth in the NDIA study that says, we're ready to move forward and to produce at scale capabilities that our warfighting people can use today and in the future. The thing that we are pushing on right now and emphasized with this study is the demand signal. Let's put the funding behind the thought process to ensure that we can get to production at scale and improve our manufacturing and improve the collaboration that happens across the entire community, academia, industry, and the government. With that, I'd like to thank Arun and Rebecca and the NDIA team. It was a lot of fun working with you. I really did enjoy helping to tie the strings together to make the report as strong and meaningful as it was. Thank you.
Thanks, Mark, and thanks to all our panelists for joining us today. I think the report, a great job by Rebecca and her team, highlights the fact that this technology has been something that we've been thinking about for a long time, but now more than ever, it's ready to go. There's some real applications that can be brought into operational use to support our defense missions. The other thing I think that was clearly highlighted here is that there's a team both in the government side, whether it's the services, the acquisition and sustainment community, the research and engineering community, or on the industry side. We've had big contractors, medium-sized contractors, small contractors, universities all mentioned as being poised to support the department when it sends, and I think the most important phrase we heard over and over again, the market signal that we're ready to move past just R&D and into deployment. So thanks again to everyone in the audience, online and in person, for attending. Again, the link to this report is emergingtechnologies.org/directed energy. Also, we're going to post this event online on our YouTube channel for anyone who wants to see it and see themselves over and over again into the future. Please be on the lookout for our next set of events from the Emerging Technologies Institute. On January 30th is our next in our Technology 101 series. It's sort of an introductory webinar in new technology areas. That one will be on digital supply chains. Also look for information on our second Emerging Technologies Conference, again, August 7th through 9th at the Convention Center. Finally, if you're interested in having your company included in the Directed Energy Source Book, please contact us via our website or see a member of our staff today. Again, thank you all for attending, and have a great day.